Thank you. Okay, so this next talk is a little more hands-on, a little more not that super technical. If you have any technical questions, please ask them. So just very quickly, my name is Camilo. I work as an architect and developer at 24HR. I've been working with web development for 20 years. And this is a little about sound recognition and machine learning, and especially about coffee making and machine learning, because it's a great example. So, quick background. First off, as you are very aware of, we Swedes are quite obsessed with coffee. We are the 6th most drinking coffee nation in the world. I actually thought that we were much higher up, but Finland beats us for that. And at our office, we believe we have the most ways of making coffee per employee. We have 5 different ways of making coffee, and we're about 20 people. So we have this unit that doesn't exist to calculate how much, a very important unit. Maybe we should all have that. And for some reason, we are quite interested in how much coffee we drink. There is no other reason that just because it's a great thing to calculate and a great problem to solve, and of course interesting. And especially drip coffee, espresso and Nespresso. How much do we drink of all these kind of coffee? The other ones are more edge cases. And of course, if you want to solve this, there are quite easy ways of doing it. You can do it super analog. You can just calculate by writing down how much coffee you drink. That would be done in a couple of minutes, but it's obviously not technical enough for us. And you can also open up your machines, whatever machines it is, and you can put some sensors in it, and you can begin to read that output and do some calculation. It would be quite easy to do as well. A little too invasive for this example. And you could also buy one of these, and you put it in front of every machine you have, and you can calculate how much power it consumes, and depending if the boiler is running, it will consume more, which is quite easy to calculate, and then you can know how much coffee you're drinking. And the reason we didn't choose this, there are some other reasons. It is because we already done that. We do this for the drip coffee already. So every time the boiler is running, we calculate that, and we can, for example, on our information board, see how much coffee has been brewed, and we get a Slack message saying that, oh, the coffee is ready, and everyone rushes to the kitchen. So yeah, you could do that, but that's not interesting in this case. So of course, you could do it much more complicated by recording the sound of the coffee machines and actually trying to understand what they mean. And again, the most complicated way, which is more fun than maybe practical. But in this case, we can use it to learn machine learning, to understand how it works. And for us, and especially for me, I've been trying to find a good case to get into machine learning and to learn how it works without the need to download some tutorial where I don't care that much about the content. I want to have something that is actually interesting for me, even if it's trivial, like making coffee. So in this challenge, we didn't have any data at all. So we start from scratch, and that poses also some interesting questions, because even if you want to use machine learning, you might not have the data set to actually begin to use it. Not everyone has a big data set, as you mentioned that you had to start with. But if we can find the data ourselves, it's our data, we care about it. It's a little easier to understand it and to care to do something with it. And no matter what kind of data you have, if you want to solve this with machine learning, you will have the same type of questions. So for example, how much data do you need to actually get it to work? And that's something we did have no idea before we began with this. Also, what type of format can you use? I mean, we're talking espresso machines. Should we use sound? Should we just the pitch or whatever? I don't know that much about sound. But this is an important question, no matter what machine learning thing you're looking into. And what tools are there and we should use? And when you choose a tool, how do they work? What kind of input do they take? And of course, how is the end result? How can you use this when you're done with everything? Quick disclaimer, I studied math 20 years ago at the university. I've forgotten everything, sadly. So this is from a web developer perspective, nothing else. So where do you begin with this? Sound, in this case, that's our input. That's what we knew we had, and it's nice because the sound doesn't require us to do anything with the machines we had. They just stand there and they just continue to be used. And a quick search on the internet made it very obvious that a normal pattern of recognizing sound is actually to convert sound to images. Because then you can use image recognition instead of sound recognition. That's a little easier. So a typical way of using the images for sound is to use a spectrogram. And again, I don't know much about sound. So we have a guy in our office that has been a sound technician, I think. He could give me some input, but that's where it ends for me. I don't know that much. But a spectrogram is a sound representation in an image over time. So the Wikipedia example is, so you have the y-axis frequency, x-axis time, and the color symbolizes how intense the sound is, how loud it is. I don't think loud is the correct word here, but similar at least. So this is a spectrogram of a sound. And when you get to the point that you know that you can use images for sound recognition, then it's quite easy to find examples of how you can use image recognition to do something. So the hello world of machine learning is something called MNIST, where you get all these images and you try to figure out how to create a model to recognize these handwritten digits. And what's interesting for us was first off, okay, it has a suggestion on how to do a model to recognize this, but also it gave us a hint of how many data entries do we need to actually get something to work. So if you look at this, you have 10 digits. The sample data you get from NIST is around 65,000 images. So basically saying, okay, we need at least that much, 6,500 per digit. And in our case, we have sound from one machine, another machine, and then we have nothing, not brewing anything. So we have 3 different labels instead of 10. So nothing, espresso, Nespresso in our case. And we label them, as Christopher mentioned. That's one of the most important parts. We have to label the data. Of course, this means that, okay, if we just follow this way of thinking, we need around 20,000 images. And if we just don't care about the nothing, because nothing is quite easy to sample, we just put a microphone and we sample ambient sound, then we should get there. So we just talking about the 2 different labels we're talking about here. 30,000 images means quite a lot of coffee. Again, we're 20 people. I don't know how much time this would take, probably quite a while. And if there are any web developers here, you know that if it takes 6 months to do some solution, then it's probably obsolete by then. So we don't want to spend that much time to do something. So we figure out that a good espresso is made in 20 to 30 seconds. So let's split it up into seconds instead of just one chunk of sound. So you have 1 second of sound that represents whatever you want to label it with. And this is actually how it looks when you have 1 second. Well, now it's perfect. I have a black line here, but 1 second of espresso sound looks like this as a spectrogram, and that's what we aim to do. So the next step, when we knew a little about how the data should look like, we needed to collect the data, and I think this is like the major thing in machine learning. Collect all data, label it. So we had 2 entry points. We need the sound, and we wanted to make it cheap. No huge computer power, just as small as possible. We bought a Raspberry Pi, a USB microphone, and I soldered some small circuit. I don't show the other side because it looks awful. So this is the nice side of it. And basically what this does is, okay, if you press one button, you begin to record, and you label it in one way. If you press the other one, you label it another way, and you record the sound as well. Nothing more than that. And a LED, because it's nice to see that you're actually recording. Then we took and wrote some node code because we love JavaScript. And this is, I won't show that much code, but this is basically it. It's an awful code, but the idea is there. There is some other stuff around it, but basically when you press a button, you call a function, you send the label, you record the stream of sound to the SD card of the Raspberry Pi, and it will be created in a folder with that label. That's it, nothing else. Just because we like Docker, we put everything in Docker, which means that you can distribute it to many Raspberry Pis, which we didn't, but always nice to be able to do that. And then we installed it in our kitchen, like this. So this is the espresso machine. That's actually the grinder, so the Nespresso is here, and you see the tripod of the microphone there. And then we instructed everyone to press these buttons when they drink coffee. So, are you making this coffee? Press the left button. Or you're doing the other coffee? Press the right button. We realized quite quickly that we needed to stop it automatically after at least 40 seconds because people forgot to stop it, and we had like 20 hours of office noise, but that was quite easy to do. And at the end of the day, this is what we got. We got a folder structure with sound files, nothing fancy. And the only labeling we have here is, I mean, this folder, and okay, we put the label in the file name as well, but that doesn't, you don't need to do that. And I don't, just for fun, let me see if I have this correctly. This is an espresso brewing, just to compare it with an Nespresso. So you hear that there is a difference. Maybe it would be super easy to do it in another way, but again, we wanted to try machine learning. When the only thing we didn't do automatically was actually cutting out the noise before the sound and after the sound. So when I was analyzing the different sound samples, I could find stuff like this. People sing in the office, good sign maybe, yes. And 2 months later, around 2 months later, we had this much data. So 260 espressos and espressos times 25 something. Then you can add some ambient sounds to just get the nothingness of that. And we could begin to actually prepare the data for the machine learning. So we took our WAV files, we took the whole spectrogram, we split it up into seconds, and we had got a lot of these files. And this was done because we began to look at which framework to use machine learning, and the framework that we wanted to use was TensorFlow. And TensorFlow, if you don't know, it's a open source machine learning framework. I think it was created by Google first, but now it's open source, and it's normally used in Python. I don't know that much Python, and learning Python and machine learning at the same time, I prefer to just learn one thing at the time. So we fall back to TensorFlow.js, which works as well. You can't find that as many examples of Python, but normally it works as well. And we looked at how do we, with the least effort, import all the data into TensorFlow.js to begin to create a model. And we saw that the NIST example, what they did was take all their images and put them into a huge image file. So what they do is, if you have like an image, you take every line, and instead of having it like a rectangle, you put every line of the same image into one line. So that means that every pixel in the height is one representation of an image. And in our case, it looked something like this. So every line you see here is a second of sound that we recorded. And all this has to be labeled. So you have to have both this and the labeling data somehow. In this example, I think we had to write a binary file that contained an array with all the labels to import it. And when you try to gather all the data, it's very important to remember that you need both training data and test data, because that's what it uses to evaluate if your model is getting better or not. So it's important to have both sets. In our case, we say, I think, like save 15% to test and the rest is to train. And we got back to this because, again, this example, this tutorial is exactly what we wanted to try to do. Except that, okay, you have figures here with just 2 colors, we have some other stuff, but basically it's the same kind of model we're trying to figure out how to work with. And the model itself, I think with the whole machine learning, every time you get a little into it, it's demystifying a lot. I mean, for me, it's still science fiction, it's still magic, but every time I look at it, it's like, okay, no, it's not that complicated, which is kind of sad because I want to keep it as magic still. This is the model itself. So basically what it does, it takes all these pixels and just makes them into 3 outputs. That's what it does. So it this max pooling thing, it downsamples the image. This applies filter to convert a part of the image into something else, and then it continues and continues. And I can't say I know the math behind this. This is basically how it works. I think an analogy is a little like if you work with Photoshop on layers, you apply layers to convert an image from something to another thing, and then you at the end you have something else. This is basically what it does. And the training part of this, I won't go too much into the code. It's not that much. There's a lot like fluff around this to show some UI status and things like that, but it's not much. I mean, the important parts here is that we need to split the how much data should it process at the same time. You need to set the epochs, which is how many times it should iterate through all the data, and those are things that you can test. You can just change the values and see what happens. So you don't need to know that much details about this. It's just actually gather the data, label it, run it, and see what happens. And when we have all data, and this is a quite important moment because I was very excited. I put it into a browser version of the TensorFlow.js, and I let it train. So what you see here is a speed up version of the video of my computer training the model. And as you can guess, the red dots here is that it's evaluating wrongly, so it's predicting the wrong result. The greens are when it's predicting correctly, and it goes more and more into green all the time. And this took about 15 minutes on my computer. And when it's done, this is what you get. Nothing more than just 2 files, one JSON file and one binary file with all the weights. And that's it, nothing more magic than that. And but what this gives you is a prediction function. So when you set it up, you load this model and you will say, okay, here's some data. What do you think this is? And that's it. So back to Raspberry Pi. Instead of gathering the data, we switched it to begin to stream the sound. So all sound, all the time in our office. I don't think it's GDPR compliant, but it records everything all the time. Well, it doesn't record, it actually just streams it. And it converts the sound into these segments of spectrograms all the time. Converts them to base 64 because they're a little easier to send them away. And we created the model, and here we had to struggle a little because running Raspberry Pi with Docker, with Node, with TensorFlow.js wasn't super easy. The binary bindings in Node didn't work as well, so we actually removed this. I thought, okay, should I put time to actually get this to work on Raspberry Pi or actually get it to work at all? I moved this to another server, so it's just a REST API. You send data, you get an answer back, that's it. But what it does, it loads the model into this, so you send the base64 string, and back you get a probability. And this is actually the typical result of a labeling, like a classification like this. So it says, okay, it's probably a 1. And back to our labeled data set, a 1 means espresso. And this here is one of the first times we tried it. So you can see that sometimes it believes that it's something else. If you scream, it actually believes it's Nespresso sometimes. But except for those small faults, it's kind of amazing. This was my eureka moment of last year. Yeah, very interesting. And I think there are 4 big takeaways from this. And the first one is that you don't need that much computer power. Of course, if you have supercomputers, you can make this quicker. If you have lots of data, you can't maybe run it on a Raspberry Pi. But normal problems you can probably solve like this. It's actually even you can actually train a model on your phone today. Just take some pictures and it will train it. And the amount of data is interesting as well. So the second thing is that you don't actually need that much data at all. I thought that this would be a big data problem. It isn't. And I think today it's even less that you need. So yesterday I actually found this, which I will comment to later why I found this. But this is from the Google site. you should need at least 10 images to create a model for image recognition. I mean, 10 images, that's nothing. And I think this is done because what they do is that they have pre-trained models for image recognition, and then you just continue to train them, so they're prepared for this kind of data. Our model was from scratch, and we got it to work pretty well. So the third takeaway is that all these tools are free, so it's really just a matter of getting into it and beginning to test them. I haven't tested anything else except TensorFlow, and from what I understand, TensorFlow 2.0 is coming out soon. What that does compared to TensorFlow.js is that they are actually trying to be more similar to TensorFlow.js than it was before. So TensorFlow.js 1.0 is actually more similar than TensorFlow 2.0 in Python version. But I think the most important part from this is actually what this means, what the difference means between how we normally do things and doing it this way. So if you think about it, if you would solve this traditionally, you would need someone with a knowledge of sound and waves and understanding of how that works, which I definitely don't. But you would need someone that understands this much, much better. You would then need to translate that knowledge somehow to someone that can implement that. If you're lucky enough, you might have one developer that understands both, or some developers might think it's interesting enough to get into sound recognition that way. But it requires specific knowledge for these kind of problems to solve. So basically, when you're doing something, you have an idea, then you have lots of development, probably, and then you can use it because you're solving one specific thing and nothing else. If you use machine learning for these kind of things, then this switches a little because the actual bulk of work is gathering data and labeling it and formatting in the right way and maybe removing things that aren't interesting, not the development itself. The development itself is like more mechanics than anything else, and then you can begin to use it, which of course means that you can concentrate on the more important things here. And I was lucky enough to attend Google I/O 2 weeks ago or 3 weeks ago, and at one of the talks they actually showed this. So this is not open source, this is Google thing, but it is both amazing and not scary, but a little boring. So they have this service called AutoML Vision. So you actually say, okay, I want to have a machine learning, and you can choose between video, image recognition, speech, and something else. And what you do is actually create a zip file. You put some folders into it, and those folders you put images. The folder name will be the labels of the data. You upload it, you click train model, and you have a model. You don't need to specify which layers you need to have. You need to do anything, which removes all the work that I did last year. So it's kind of boring, but at the same time, it makes it really accessible to anyone. So you have data, you have labeled data, you can train it. And it works so that you can either tell it to train a model and download it to your computer later to use it on a Raspberry Pi or a phone or whatever offline, or you can train a model to actually run the model itself on their cloud system, which gives you an API, REST endpoint. So when it's trained, you just post a request and back you get the result. And this worked at least as good as the one I did, which again, we spent quite a lot of time to try to do most of the time is to actually get the data. Of course, that doesn't disappear, but it's as simple as it has ever been to do this. So it goes back to where you put your time. Do you want to develop a lot, or do you want to just use whatever idea it has? So the result for me, it's still a lot of magic. I think if I just don't think too much about the algorithms and the math behind it, because it loses a little of the sci-fi in it. I just think about the result. I think this is crazy what we can do. And again, I can create a model of something that I have no knowledge of. I just have the data, and I think that's the big difference. You don't need to have a person that specializes in sound or whatever it might be to create it. And that's it.